Hello everyone. For this video, I'm going to be covering the very beginning of Chapter 2, in which we dive a little bit deeper into matter and what all of it really means and what we're going to be focusing on for the remainder of the semester pretty much. And so the first thing we have to do before we actually start talking about matter is kind of break it down into what we call the different kind of types. And so the first thing we have to kind of, discuss here is there are only really three, I'll grant it, maybe three and a half different types of matter. And so each of these different types of matter are kind of different in how they are composed or what they are composed of. And so the first type of matter we're going to be coming across a lot during this semester is what we refer to as elements. And so if we were in the classroom right now, I would be pointing at this giant thing on one of the walls at least that is called the periodic table of elements. And so every single one of those things on that periodic table are what we call an element. And so an element is unique in the fact that it is only composed of one type of atom. And so when we kind of go through and start talking about these things, elements are just it. They're it. They can't be anything else besides an element, meaning the fact that they are the simplest form of matter. They can't be broken down into anything else because as soon as you have a sample of carbon, you can't smash that carbon down and get anything else except for carbon atoms. And so please note, an element is only one type of atom, just repeating itself over and over and over again. For example, all of us love gold, and if you go out and you buy like the jeweler tells you is 100% gold, then you're safely assuming that every single one of those atoms in that piece of gold is going to be a gold atom. If not, if you have one of those atoms happen to be an iron atom per se, then you're not looking at an element anymore. Now you're looking at something that contains some type of impurity, so therefore it is not a pure element. And so the other half of this is what they refer to as molecular elements. And so sometimes you'll come across some atoms that just do not like to be by themselves. Hydrogen and oxygen are the ones you're probably more familiar with, but elemental hydrogen is H2. Elemental oxygen is O2. These guys will never be by themselves. You'll never find an individual H just floating around. And again, under some unique circumstances, yes, but in the environment naturally occurring, you will never find just an H by itself. The same thing with O or N or S. You will never see these atoms by themselves. They will always be teamed up or grouped up, but they're always going to be grouped up with another atom of themselves. And so hydrogen is still composed of just a single atom repeating itself. It just happens to have a partner the whole time it's repeating. And so we still call these elements, but because they are two or more atoms put together, they are called molecular elements. But please note, because I know some of you are listening to me, but you're still going to forget, but H2 and O2 are still pure elements. They are just molecular elements, whereas vice versa with these guys here, these are what they call atomic elements. And so atomic elements, single atom repeating themselves over and over and over again. You can have a single atom of gold that exists somewhere in the universe. Whereas these guys, you'll never find a single atom of H or a single atom of O. They're always going to be paired up. And the next kind of type we're going to talk about for a couple times is going to be a compound. And so a compound is whenever you have two or more elements take that back. Two or more different elements that are combined, typically through some type of chemical process. And so most of these, again, are going to be atoms of two different types, up to however many different types of atoms, but they're going to be combined. But more specifically, they are combined in a very, very oriented structure. And so by that I mean H2O has to be in the form of two hydrogens with one oxygen, but in also has to have these two hydrogens at very specific arrangement, very specific angles around this oxygen, so on and so forth. And so compounds, they are composed of two or more elements, but they're also in a very nice, neat package and very nice arrangements. And again, if these arrangements are off, a lot of different things can go wrong there. And the last type of matter we're going to talk about, or I guess we kind of talk about them, but more or less it's everything else that doesn't fall into those two categories. And so mixtures are whenever you have elements or compounds or a mixture of elements and compounds and dirt and air and everything else. A mixture is just a whole bunch of stuff thrown into a mixing pot. And so a good example I always use in like class is talking about chili. And so again, I have a recipe for chili. You might have a recipe for chili, and your grandmother might have the best recipe for chili in the world. And all of them typically contain meats and beans and veggies and tomato sauce, but the proportions might be a whole lot different. I mean, I might put one bean inside of mine and have all of it meat and tomato sauce. Whereas again, some of you like to throw in all those nasty green vegetables and everything. But hey, to each their own. But in this case, all I'm trying to state is the fact that mixtures do not care about proportions. Something like air, the air you breathe in whenever you're sitting inside your house, is going to have different amount of oxygen and hydrogen and N2 and carbon dioxide than the air you breathe outside, than the air you breathe on top of Mount Fuji. In all these cases, it's still classified as air. It's just going to have a lot of different amounts of different compounds in there. And so, now that we got that out of the way, the next thing we have to kind of talk about is how all these rules kind of came about. And so the first guy we have to talk about is Anton Lavoisier. And so Anton Lavoisier came up with this idea of law of conservation of mass. And so all that really means is in a chemical reaction, even though things seem to kind of change and some things quote unquote disappear, in a chemical reaction, matter cannot be created nor destroyed. Meaning the fact you cannot break up matter and have it disappear. It has to go somewhere. And so the whole idea behind this is all matter is composed of of atoms. And so if all atoms are indestructible, then you can't destroy matter. In addition to that, no matter how much you stare at your empty hand and wish and wish and wish, a pile of gold just can't just appear out of nowhere in your hand. And so when these chemical reactions occur, even though it looks like there's some change, a good example of this is like burning a piece of firewood. And so if you burn a piece of wood, at the end you end up with ash that seems a lot lighter than that huge chunk of wood you burned. But you have to remember that when you burn wood, you also release gases. You also release a bunch of ash that flew away in the air. And so in these cases, the chemical reaction does not do anything to that matter. All it does is rearrange those atoms. It might break apart some atoms, but it does not just make those atoms disappear at all. It has to come to like same equality on both sides. A great example of this is if we're doing a chemical reaction with sodium and chlorine. And so in this case, and I'll kind of talk about this a little bit more in detail on coming up slides, we are looking at an ionic reaction. And so if you take sodium, which is a shiny metal, and you take chlorine, which is a yellow gas, and you mix them together, we end up creating sodium chloride, which we all normally call salt. But in this case, if you mix 7.7 grams of sodium and 11.9 grams of chlorine, which is total 19.6 grams of sodium and chlorine together, you better end up with 19.6 grams of sodium chloride. If not, then you're violating some laws of science, and that usually creates black holes that we're not really trying to do. And so the next guy we have to talk about is Joseph Proust, who in 1797 kind of came up with a really weird rule whenever I kind of explain it to you. And again, in our time, it makes total sense. But back in 1797, when things were kind of still being figured out, this is still kind of like great big news for everybody. And so what Joseph Proust basically stated is that if you have a compound and you want to call it, say, water, then you better have every characteristic of every other sample of water you've ever found. And so meaning that if you want to call something water, it better contain 2 hydrogens and 1 oxygen. It better contain the specific atomic ratios and mass ratios. It better also have the same freezing point, melting point, density, everything else that we have defined water has to have. If you want to call some other sample water, it has to be that same exact kind of quality. And so in this situation, it doesn't matter if you found this water underneath your porch, or if you created the water in the lab, or if you someday at some point in the future find a huge lake on Mars. If we want to call that liquid that we're playing with water, it has to be water in all characteristics. And so he called this the law of definite composition. And so please note here, I've kind of stated multiple times water, water, water. I have not told you any other compounds. And so the law of definite compositions is talking about only one type of compound. And so you can have several samples of that one compound, but we're still just talking about one thing. And so the great thing about that is if we have one sample that we know a lot of information about, that means all the other samples of that type of compound also have to have that same situation set up. And so in this case, if we know a chemical formula for water, we know the chemical formula for all samples of water is going to be the exact same chemical formula. And if we know the formulas or if we know the number of atoms, then we can figure out something about all that mass that's kind of going along here. And so I show these two equations here. Don't freak out. I'll explain them more in these next two slides. But the mass ratio of whatever you are looking at or whatever element you're looking for is going to be the mass of that element in the compound over the mass of the total compound. And same deal with the mass of the element in the sample. If you have that mass fraction, or in this case, if you know the percentage of that element inside of that compound, you multiply it by the given mass of the compound and you have the mass of the element. I know it seems kind of confusing, so let's look at this example right here. And so as I kind of mentioned earlier a couple times, water can only be called water if it has 2 hydrogens and 1 oxygen. If it freezes at 0 degrees Celsius, if it boils at 100 degrees Celsius, if it has the density of 1.0 grams per milliliter. And so all of these kind of go hand in hand, that if you want to call a puppy, it better look like all the other puppies we've seen and not be an alligator. And so in these cases, if we know this information about one sample of water, we know the same information has to apply to every other sample of water that we want to call water. And so we know it has to have 2 hydrogen atoms and 1 oxygen atom. We know the molecular mass has to be 18.02 grams because each hydrogen is 1.01 and the only oxygen is going to be 16 grams per mole. And so because of this, we know the atomic mass ratio of this must be about 2.02 grams of hydrogen for every 16 grams of oxygen, or the mass of 2 hydrogen atoms, the mass of 1 oxygen atom. We also know because of these ratios, we have to have 2 hydrogens for every 1 water, or the mass of 2 hydrogen atoms for the mass of our water, or 2.02 grams of hydrogen for 18.02 grams of the water. Same deal for the oxygen. 1 oxygen for every H2O, because there's 1 oxygen in H2O. So you have to have 16 grams of oxygen for every 18.02 grams of H2O. And luckily, if you know this, then we can do math with any sample size of water. And so we can figure out the mass of any hydrogen, or mass of hydrogen, or the mass of oxygen in any sample. And so just a random number that I kind of started just typing out, but 72.08 grams of water, we know it contains the same number of oxygens and the same number of hydrogens as every other sample of water. And so we know it has to have the same ratio of hydrogens and oxygens to your water. So here, the mass ratio of my hydrogen to my water is going to be the 2.02 grams of hydrogen for every 18.02 grams of water. So use that mass ratio and multiply it by the 72.08 grams of your compound, and you end up with 8.08 grams of hydrogen. Similarly, do the same thing with the mass ratio of oxygen. We have 16 grams of oxygen for every 18.02 grams of water, so that's our mass fraction of our water, or mass ratio of water. Oxygen in water. And so multiply that by the mass of your sample size, and you have 64.00 grams of oxygen. And just to prove what I said previously is correct, using the law of conservation of mass, if I have hydrogen plus oxygen, you know that mass of hydrogen and oxygen better be equal to the mass of our water, which luckily it does, so we have not violated any laws yet. So here's another example. If we have a 26.8 gram sample of silver bromide, and it contains 15.4 grams of silver, with bromine being the only other element, how many grams of each of the elements are in the sample that contain 3.57 grams of silver bromide? So in this case, I kind of color coded it for you to hopefully kind of guide you through this process here. But if we're trying to look for how many grams of each element, the first thing you need is some type of mass ratio or mass fraction of those elements. And so here, using the definition I gave previously, we know the mass fraction is going to be the mass of the element in the compound divided by the mass of the compound. And so the mass of silver is going to be very easy because I give you both of these already. And so the mass fraction of our silver is going to be our 15.4 grams of silver that is going to be inside of our 26.8 grams of silver bromide. And so here I'm not going to break it down anymore just so I can show you where I'm plugging these values in. But you are now looking at the mass fraction of silver. And so if we want to know the amount of silver inside of our new sample size of 3.57, we know this mass ratio is still going to be the same regardless of what your sample size is. And so here, just using the same kind of setup from previous slide, if you want to know the mass of your silver, you're going to take the mass of your 3.57 gram sample of silver bromide and multiply it by the known mass fraction of our silver in order to get 2.05 grams of silver. So the other half of this problem is talking about the other element that's inside this compound. And so in the problem, I tell you this stuff is silver bromide containing a given amount of silver, but bromine is still there without a certain given amount. And so in this case, you have to take into consideration what I've talked about on the previous slide and previous couple slides of the law of conservation of mass. So the law of conservation of mass states that the mass of the reactants better equal the mass of your product, or the mass of the silver plus the mass of the bromine has to equal the mass of the silver bromide. And so if you subtract these two values, the mass of your silver bromide minus the mass of the silver, you get the mass of your bromine. And then using the mass of your bromine over the mass of your silver bromide, you end up with the mass fraction of your bromine multiplied by the mass sample that we're given now, and now you have a new sample size of 3.57 grams. And so 2.05 plus the 1.52, if you want to plug that into your calculator real quick, and believe me, it's going to be the same 3.57. So, if you thought that was fun, let's get to this last law we have to talk about. And so if you read over this slide faster than I talk, you're going to be confused, so just listen to me here. And so in 1804, John Dalton, we'll talk about him more in the next video, came up with one of the most confusing backwards way of saying something makes total sense. And so the law of multiple proportions states that if you have two elements that combine to make multiple compounds, and again, by multiple compounds, I mean you have AB1 and AB2 and AB3. Each of these, this one contains one B, that one contains two B's, that one contains three B's, but it's still a combination of just your A and your B. If they combine to make multiple compounds in that format, the mass of B that reacts with a fixed amount of A is always going to be related to one another in small whole number ratios. And so, first thing I have to say before I explain this a little bit more detail is let me go back to this problem here. In this problem, I talk about a 26.8 gram sample of silver bromide. I then talk about a 3.57 gram sample of silver bromide. In the previous example, I talked about water, then I talked about water, and I talked about water. And so please note, in both of these examples, I only talk about one compound. I talk about multiple samples, but I am still just talking about one compound. Whereas in multiple proportions, multiple means more than one. And so in this case, I am talking about, listed even here as three different compounds, AB1, AB2, and AB3. And so if you're given a problem on a homework or on an exam, and it asks you to identify which law you're talking about, the law of multiple proportions better be talking about multiple things. Whereas the law of definite compositions or proportions is talking about one compound, maybe several samples, but it's still several samples of water. And so one last thing before we kind of move on about all this stuff is the law of definite composition has a huge tie into all of these like other laws. And so again, one thing you should start noticing about chemistry is they build upon each other. All right. So what all of that stuff meant on the previous slide is if I have two elements, in this case I have carbon and oxygen, and if they combine to form more than one compound, or in this case carbon monoxide and carbon dioxide, and theoretical carbon trioxide, which doesn't exist, but in this case you're looking at each of these compounds as composed of just carbon and oxygen. Additionally, each of these three compounds has one carbon and differs in only the number of oxygens. And so if we look at the ratios of oxygen to carbon, we can kind of see some type of relationship that I'm talking about when I refer to the law of multiple proportions. And so here, to give you a better idea, I kind of broke it down. So each sample contains 12.01 grams of carbon. And in that previous slide, this is what I'm going to call my A. And so each sample contains different amount of oxygens, which should make sense because they contain different numbers of oxygens. And so when we kind of go through and look at this, as the law of multiple proportion states, if you have the amount of B that interacts with a fixed amount of A, or the amount of oxygen that interacts with a fixed amount of carbon, will be related to each other by a whole number ratio. So in order to check that out, we have to look at the oxygen to carbon ratio in this first one, or 16 divided by 12.01 gives you 1.33. Then in our carbon dioxide, we have 32 divided by 12.01 to give you 2.66. Or in this third make-believe carbon trioxide, we are given a oxygen to carbon ratio of 3.99. And so if you kind of take a look at these ratios here, what is the relationship between 1.33 and 2.66? Don't pull out a calculator. I'll tell you, it is a 1 to 2 relationship. And should make sense because in carbon monoxide, we have one oxygen. In carbon dioxide, we have two oxygens. And take it one step further, what is the relationship between 1.33 and 3.99? And if you look at here, it's a 1 to 3 ratio, which again should make sense because there's one oxygen here and three oxygens here. And so in these situations, you just need to kind of understand how we're going about these things. And so the main thing I can tell you about these laws is you do need to know them. They will show up on the exams. Just understand the law of definite composition, or law of, I'll go back to it so I say whatever I said here. The law of conservation of mass is always going to have to deal with all chemical reactions. A plus B gives you C. The mass of A plus B has to equal C. And then when we talk about the law of definite composition, we are talking about multiple samples of one and only one compound. And so again, if you find a sample of water underneath your porch, if you create a sample of water in in the lab, or if you find a sample of water on Mars, they're all going to have the same definite proportions and ratios and densities and everything else. But we're still talking about just one thing. And the last one, again, we start talking about, the law of multiple proportions, we are talking about multiple things. Same two elements, or maybe three elements if you want to get fancy, but same two elements, but in multiple compounds. Hopefully that clears things up, and again, look forward to talking to you all in class.